In this video, we are going to discuss about derivation of constant elasticity of substitution production function. Graphically, the optimal position of a firm is shown by the tangency point between the isoquant and the factor price line as shown here. Mathematically, the elasticity of substitution is defined as proportionate change in capital labor ratio over proportionate change in marginal rate of technical substitution of labor for capital, where MRSLK is equal to marginal product of labor divided by marginal product of capital, or the partial differentiation of our production function with respect to labor divided by the partial differentiation of our production function with respect to capital. Now, at optimal point, the negative of delta K over delta L is equal to f of L over f of K is equal to MPL over MPK, which is equal to PL, price of labor, divided by price of capital, is equal to wage over rent. Now let capital labor ratio is denoted by U and MRS is denoted by M. Putting this notation into elasticity of substitution equation, we get sigma is equal to delta U over U all over delta M over M is equal to sigma is equal to delta U over delta M times M over U, or du over U is equal to sigma, which is elasticity of substitution, times dm over m. Of course, we took limiting case where delta m approaches to 0. Now, taking the equation du by u is equal to sigma times dm over m, integrating both sides, we get integration of du over u is equal to sigma, which is elasticity of substitution, times integration of dm over m. Now, simplifying it will give us integration of 1 over u times du is equal to sigma times integration of 1 over m times dm. We took elasticity of substitution here as constant. Now, the integration of 1 over u times du is nothing but log u, and sigma times integration of 1 over m times dm is nothing but sigma times log m plus log c, where log c is the arbitrary constant of our integration. Now, taking anti-logarithm on both sides, we get u is equal to c times m power sigma. Now, what are the interpretation of this tiny beautiful equation? Here, U is the capital labor ratio and M is the ratio of prices of factors of production. Now, if C is greater than 0 for certain production function, let's say, then all such production function must have the property that capital labor ratio is proportional to the factor price ratio raised to some power, and that power will be the elasticity of substitution of that particular production function. Now, re-evaluating the term for U and M, we get K over L is equal to C times f of L divided by f of K whole raised to power sigma, which is equal to sigma root of k over L is equal to z times f of L divided by f of k, where z is equal to sigma root of c, which can be written as k over L raised to power 1 over sigma is equal to negative of z times delta k over delta L, since at the optimal point negative of delta k over delta L is equal to f of L over f of k. Since z is a constant and may take the value 0 to infinity, let us take z in terms of another constant. Let's say z is equal to 1 minus alpha over alpha, where alpha is between 0 to 1. Therefore, z is between 0 to infinity, so no generality is lost. Now, incorporating the new value of z into our equation become k over L raised to power 1 over sigma is equal to negative of 1 minus alpha over alpha times del k over del L. Regrouping k over L to the power 1 over sigma give us 1 over L to the power 1 over sigma times k to the power 1 over sigma is equal to negative of 1 minus alpha over alpha times del k del L. Now, rearranging those terms, we get alpha times del L over L to the power 1 over sigma is equal to negative of 1 minus alpha times del k over k to the power 1 over sigma. This is the partial differential equation we are looking for. By taking sigma as 1, the resultant solution will be the Cobb-Douglas production function. And all those cases where sigma is not equal to 1, the resultant solution will be the constant elasticity of substitution production function. Rearranging and taking the integral on both sides, we get this result. What is the h of y here? Well, since we are dealing with partial differential equation, the arbitrary constant of integration may involve any function of variable or variable held constant. Remember, we determined negative of del k del L along the same isoquant, in other words, output held constant. So, our arbitrary constant will be some function of output, and that is what this h of y is. The denominator cancels out here, and h of y will not affect it because we have just said that this is arbitrary constant, which is some function of output. If we divide that constant with another constant, the resultant will be another constant, which will be certain function of the output, so no generality is lost. Simplifying and taking rho is equal to 1 minus sigma over sigma, so sigma become 1 over 1 plus rho, replacing rho for 1 minus sigma over sigma. Since our production function is homothetic by assumption, indeed assuming h of y is monotonic, we can write therefore y as follows, where f is the inverse function of h. Now, if we insist our production function to be homogeneous of degree 1, we can write y, which is output, as follows. This is the general form of production function of what we call constant elasticity of substitution production function. Similarly, we can derive the Cobb-Douglas production function from the partial differential equation 2 by simply taking sigma, which is elasticity of substitution, as 1. Please check out for the next video, where I am going to explain the meaning of elasticity of substitution, constant elasticity of substitution production function, Cobb-Douglas production function, their implication, their relationship with a graphical visualization technique. Thank you.